There are two primary options to achieve the described control wiring scenario. Option 1 involves using an auxiliary contact. Firstly, add an auxiliary contact, specifically a 13-no, to the contactor. Secondly, connect the 13-no contactor in parallel with the normally open contact designated as A1 on the contactor. Thirdly, wire the 324 volts DC valve control wires in series to the auxiliary contact, the 13-no contact. The functionality is such that when any of the three valves are energized, the auxiliary contact will close and power will be supplied to the blower motor through the normally open contact A1. Option 2 involves using a control relay. Firstly, use a control relay equipped with three normally open contacts. Secondly, connect the 24 volts DC valve control wires to the relay coil. Thirdly, connect the normally open contacts of the relay in parallel to supply power to the blower motor. In this setup, when any of the three valves are energized, the relay coil will be energized, causing the normally open contacts to close, thereby providing power to the blower motor. Beyond these two options, several additional considerations are important. Firstly, ensure that the voltage rating of the auxiliary contact or relay coil is compatible with the 24 volts DC supply used for the valves. Secondly, use wire sizes appropriate for the current they will carry, and ensure proper insulation and termination practices are followed. Thirdly, thoroughly test the circuit to verify that the blower motor operates as intended whenever any of the three valves are energized. To elaborate, selecting the correct wire size is crucial for safety and performance. Consult the National Electrical Code, NEC Table 310.15 or equivalent standards to determine the appropriate wire gauge based on the anticipated current draw of the blower motor and the ampacity of the wire. Pay attention to the insulation type of the wire as well, ensuring it is suitable for the environmental conditions within the control box and the temperature rating of the connected devices. Proper termination involves securely connecting the wires to the terminals of the contactor, relay, and other components. Use appropriately sized crimp connectors or terminal blocks, and torque the connections to the manufacturer's specified values to prevent loose connections, which can lead to overheating and potential failures. When implementing either the auxiliary contact or control relay method, consider adding overcurrent protection for the blower motor circuit. This can be achieved by installing a correctly sized fuse or circuit breaker in the 480 volts power feed to the contactor. The overcurrent protection device should be sized according to the motor's nameplate current rating and any applicable codes or standards. In addition to overcurrent protection, it may be beneficial to incorporate surge protection devices into the control box. These devices can help protect the control components from voltage spikes and transients, which can be caused by lightning strikes, switching operations, or other electrical disturbances. Surge protection is especially important in environments where the power supply is prone to fluctuations or where sensitive electronic equipment is present. Furthermore, consider the layout and organization of the control box to facilitate easy maintenance and troubleshooting. Use wire ducts or cable ties to neatly route and bundle the wires, and label each wire and component clearly. This will make it easier to identify and trace circuits when performing diagnostics or making modifications in the future. It is also important to ensure that the control box is properly grounded to provide a safe path for fault current. Connect the control box to a suitable grounding electrode system, following the requirements of the NEC or other applicable standards. The grounding conductor should be sized appropriately for the size of the power conductors feeding the control box. When wiring the 24 volts DC control circuit, pay attention to polarity and ensure that the positive and negative wires are connected correctly. Incorrect polarity can damage the control components or cause the circuit to malfunction. Use color-coded wires to help maintain consistent polarity throughout the circuit. Also, consider using shielded cables for the 24 volts DC control wires to minimize the effects of electromagnetic interference. This is especially important in environments where there are high levels of electrical noise or where sensitive electronic equipment is located nearby. The shield should be connected to ground at one end only to prevent ground loops. When testing the circuit, use a multimeter or other appropriate test equipment to verify that the voltages and currents are within acceptable limits. Check the voltage at the relay coil or auxiliary contact to ensure that it is within the specified range. Also, measure the current draw of the blower motor to ensure that it is not exceeding its nameplate rating. If any abnormalities are detected, troubleshoot the circuit to identify and correct the problem. In addition to the electrical considerations, also take into account the environmental conditions in which the control box will be installed. If the control box is located in a damp or corrosive environment, use enclosures and components that are rated for those conditions. Also, consider providing ventilation to prevent overheating of the components inside the control box. This can be achieved by installing vents or fans to circulate air through the enclosure. Finally, always follow safe electrical work practices when working on the control wiring. To energize the circuit before making any connections or modifications, and use appropriate personal protective equipment such as insulated gloves and safety glasses. If you are not comfortable working with electricity, consult a qualified electrician. Remember that the auxiliary contact method provides a simple and cost-effective solution for controlling the blower motor based on the valve status. The auxiliary contact is wired in series with the valve control signals so that when any of the valves are energized, the auxiliary contact closes and the blower motor is activated. This method is suitable for applications where the blower motor is relatively small and does not require precise control. The control relay method offers greater flexibility in control over the blower motor. The control relay can be used to provide isolation between the valve control signals and the blower motor, which can be important in applications where there are differences in voltage levels or where there is a risk of electrical noise. The control relay can also be used to implement more complex control functions such as time delays or interlocking. When choosing between the auxiliary contact method and the control relay method, consider the following factors: the size and power requirements of the blower motor, the voltage levels of the valve control signals and the blower motor power supply, the level of isolation required between the valve control signals and the blower motor, the complexity of the control functions required, the cost of the components, the ease of installation and maintenance. In general, the auxiliary contact method is a good choice for simple applications where the blower motor is relatively small and does not require precise control. The control relay method is a better choice for more complex applications where the blower motor is larger or where precise control is required. Also, note that the type of auxiliary contact that is added to the contactor should be a normally open contact. When the contactor is not energized, the normally open contact will be open, which will prevent the blower motor from running. When the contactor is energized, the normally open contact will close, which will allow the blower motor to run. The auxiliary contact should be rated for the voltage and current that it will be switching. The wire size used for the auxiliary contact should be sized appropriately for the current that it will be carrying. In regards to the control relay, a 24 volts DC coil relay with contacts rated for the blower motor voltage and current should be selected. The relay contacts are wired in parallel with the valve control signals so that when any of the valves are energized, the relay contacts close and the blower motor is activated. This method provides electrical isolation between the valve control signals and the blower motor, which can be important for safety and reliability. The relay should be mounted in a suitable enclosure to protect it from the environment. The wiring should be neatly routed and secured. All connections should be tight and properly insulated. After the wiring is complete, the circuit should be tested to ensure that it is working properly. The blower motor should start and stop when the valves are energized and de-energized, respectively. Remember to consult the blower motor's nameplate for voltage, amperage, and any specific wiring instructions. Adhere to local and national electrical codes during the wiring process. Consider labeling all wires and components for easy identification during future maintenance. Implement safety measures like fuses or circuit breakers to protect the motor from overcurrent. Verify the correct operation of the system under various conditions after installation. When using a control relay, consider adding a flyback diode across the relay coil to protect the control circuit from voltage spikes when the relay is de-energized. The diode should be connected in reverse polarity across the coil, with the cathode connected to the positive side of the coil. If multiple control relays are used, ensure that they are properly coordinated to prevent conflicts or race conditions. This may involve adding time delay relays or interlocking circuits. Consider using a programmable logic controller (PLC) to implement more complex control functions. A PLC can be programmed to monitor the valve control signals and control the blower motor based on a variety of factors, such as time of day, temperature, or pressure. This can provide greater flexibility and control over the system. When designing the control system, consider the potential for future expansion or modification. Use modular components and wiring techniques that will allow for easy addition or removal of components. Also, document the control system thoroughly, including wiring diagrams, component specifications, and programming code. When troubleshooting the control system, start by checking the power supply and control signals. Verify that the correct voltages are present and that the signals are being transmitted correctly. If the power supply and control signals are okay, then check the individual components, such as the relays, contactors, and sensors. Use a multimeter or other test equipment to verify that the components are functioning properly. If a component is found to be faulty, replace it with a new one. After replacing a component, retest the circuit to ensure that it is working properly. The National Electrical Code, or NEC, is a widely adopted standard for electrical wiring and safety in the United States. It is important to consult the NEC when designing and installing electrical systems to ensure that they meet the minimum safety requirements. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is important to be familiar with the NEC requirements that are relevant to your specific application. Another helpful resource is the National Electrical Manufacturers Association, or NEMA. NEMA is an organization that develops standards for electrical equipment. NEMA standards cover a wide range of products, including motors, contactors, relays, and enclosures. When selecting electrical equipment, it is important to choose products that meet NEMA standards to ensure that they are safe and reliable. Electrical safety is paramount when working with electrical systems. Always follow safe work practices and use appropriate personal protective equipment. Never work on live electrical circuits unless you are qualified and authorized to do so. If you are not comfortable working with electricity, consult a qualified electrician. The choice between using an auxiliary contact or a control relay depends on the specifics of the application and the desired level of control and isolation. Both options can provide a safe and reliable way to control the blower motor based on the state of the 24 volts DC valves. Before beginning any electrical work, ensure that the power is turned off at the circuit breaker or disconnect switch. Use a voltage tester to verify that the circuit is energized before touching any wires or components. Wear appropriate personal protective equipment, such as safety glasses, insulated gloves, and appropriate clothing. Work in a well-lit and dry environment. Do not work on electrical systems in wet or damp conditions. Keep your work area clean and organized. Do not leave tools or debris lying around that could create a hazard. Use the right tools for the job. Do not use tools that are damaged or in poor condition. Follow the manufacturer's instructions when installing or using electrical equipment. Do not overload electrical circuits. Know the current carrying capacity of the wires and components you are using. Inspect electrical systems regularly for signs of wear or damage. Replace any worn or damaged components promptly. If you are not comfortable working with electricity, consult a qualified electrician. Do not attempt to repair or modify electrical equipment unless you are qualified to do so. When working with electrical systems, it is important to be aware of the potential hazards and to take steps to protect yourself and others from harm. The auxiliary contact is a simple and cost-effective solution for controlling the blower motor. The control relay provides greater flexibility and control. Choose the method that best meets the needs of your application. Always follow safe electrical work practices. Using wire nuts for electrical connections is a common practice, but they must be applied correctly to ensure a safe and reliable connection. Firstly, strip the insulation from the ends of the wires to be joined, exposing enough bare wire to be securely gripped by the wire nut. The amount of insulation to remove is usually indicated in the wire nut packaging. Secondly, hold the bare ends of the wires together, ensuring they are aligned in parallel. Twist the wires together tightly in a clockwise direction. This creates a mechanical connection that will help to prevent the wires from pulling apart. Thirdly, push the twisted wires into the wire nut and twist the wire nut clockwise until it is snug. The wire nut should grip the wires tightly and not be easily pulled off. Finally, tug on each wire individually to ensure that the connection is secure. If any wire pulls out, repeat the process and tighten the wire nut further. It is important to use the correct size wire nut for the number and gauge of wires being joined. Using a wire nut that is too small can result in a loose connection, while using a wire nut that is too large can result in the wires not being properly gripped. Consult the wire nut packaging or a wire nut sizing chart to determine the correct size for your application. When using wire nuts, it is important to follow a few safety precautions. Firstly, always turn off the power to the circuit before working on any electrical connections. Secondly, use insulated tools to prevent electric shock. Thirdly, inspect the wire nuts regularly for signs of wear or damage. Replace any worn or damaged wire nuts promptly.